Yeah, and our next talk is by Christian Basteck. Christian, please, the screen is yours.
Okay. I guess now you can hear me. So, yeah.
We can't hear you.
We lost you again.
Okay. Okay. Thanks everyone for tuning in. I will present some recent work of Lars and me on Lars Ehlers and me on strategy-proof envy-free random assignments. Does it? Yeah, this pandemic hasn't been going on long enough for me, I think. Okay. I think the main problem is more than familiar to all of you. We want to assign indivisible objects where each agent is to receive at most one object. And what makes the problem interesting is the fact that agents have preferences that are private information. Right? So if we now think about classical 3 objectives for allocation problems, first one, of course, efficiency. That would be, we want to assign objects in line with individuals' preferences, of course, as much as that's feasible. Second, because preferences are private information, we have to think about incentives of individuals to reveal their preferences. Ideally, we would like to have a strategy-proof mechanism, or perhaps something even stronger, as we were just reminded. And third of all, we would like to have some degree of fairness, in particular, if we think about objects that are just allocated, where there's no initial property rights, that basically comes down to we want to treat individuals equitable, equally. And there, of course, the fact that objects are considered to be indivisible creates huge problems. So what we typically do then is we move on to random assignments where we can adjust probability shares a bit more freely and hence achieve equity in some sense. Now, there are, however, several fairness concepts, and the one that we will consider in this work is the one that also, well, it's a fairly strong one, but I would argue a fairly compelling one, namely envyfreeness. In particular, what do we want to look at? We asked the following question. Suppose you take the incentive problem seriously in that you demand strategy-proofness. Suppose you also take the fairness problem really seriously in that you demand envyfreeness. Every individual should feel that from an ex-ante point of view, they are at least as well off as anyone else. Given these constraints, how much efficiency can you really get? Right? And what we find here, what we provide is a quantitative upper bound on the efficiency that you can achieve. And we show that this bound is tight in that we provide a simple mechanism that actually achieves this bound. Okay. Brief reminder of some related results. If you start out with requiring strategy-proofness, then random priority or random serial dictatorship is a very valid starting point. What does it achieve in terms of fairness? Okay. No, I think school choice is a bit further down. Okay. Yes, what does it achieve in terms of fairness? We have equal treatment of equals. So at least for individuals who are identical in terms of their preferences, there we constrain the outcome for these two individuals in that they should be treated the same. And moreover, we achieve exposed efficiency. Now, what was already pointed out, 20 years ago now that random serial dictatorship, but also any other such strategy proof and mechanism that satisfies equal treatment of equals will not be efficient from an ex-ante point of view. Further, if we feel that equal treatment of equals, because it only applies when individuals have exactly the same preferences, is a bit too weak, and we would, for example, move on to envy-free mechanisms, then we further have to reduce our expectation in terms of efficiency. We cannot even get exposed efficiency then. And third, if we also consider the domain where objects may be unacceptable, then we've learned from Martini that a mechanism that is strategy proof and satisfies equal treatment of equals will also be wasting objects from an ex-ante point of view if you consider the probability shares. I will skip over the grayed out part, just mention that there are two recent papers that follow similar approach to us, or that are interested in actually the very same problem, I might say. Namely, they ask how much efficiency can you get if you insist on strategy proofness and envyfreeness, and I will comment on the overlap once I get to the results. Okay, there's nothing surprising in the model, so let me be quick. We have a finite set of objects and agents. We assume they're of the same size. We assume preferences are strict. For most of the talk, I will just consider the domain where all objects are considered acceptable. So that's denoted R lower bar N. Then an assignment is just a mapping of agents to objects that they receive. You can think about the set of all possible assignments. You can think about probability distributions over that, namely random assignments then. And we assume that individuals compare random assignments based on stochastic dominance. Right? So consider one random assignment better than the other if it gives you a weakly higher chance of receiving a most preferred object and a weakly higher chance of receiving either of your two most preferred objects, and so on. Last thing on last slide on the model, a mechanism will then just be a mapping of preference profiles to such random assignments. And mechanism is strategy proof if submitting your true preferences always makes you weakly better off in this stochastic dominant sense than submitting anything else. Finally, the mechanism is envy-free if the individual random assignment that you get is at least as good in terms of stochastic dominance again as the random assignment that anyone else gets. Okay, now on to the first impossibility result. One more piece of notation. Let me just denote by O upper bar I the top object of individual I. And as I said, for most of the part now, for most of the remainder, let's now just assume that all objects are acceptable. Then perhaps, or not perhaps, but arguably the simplest problem to solve are those preference profiles where we all have a different first most preferred object, right? Then everyone should just receive the most preferred object and go home. There's one assignment that does this. There's unanimous agreement that this is the best. So whenever we have such a special preference profile, then everyone should receive the most preferred object with probability 1. Now, I warned you, it would be an impossibility result. Already with 3 objects and agents, it's impossible to have strategy proofness, envyfreeness, and this unanimity. Another way to think about this here is unanimity really is weakening exposed efficiency to apply at least at these special preference profiles. That's another way to think about it. Okay, so, and this is exactly what was found independently also by Priyanka Shende and Manish Purohit in their paper, and also by J. Siddharaman. So I wanted to present this a year ago, had sent it off, but Lars and I only managed to prepare the working paper in December. And once we had that out, we got contacted by Priyanka, and she said, "Oh, that's a nice paper, but you know what? We find the same thing." And a little while later, J. Siddharaman also contacted us and said he had been in contact with Priyanka as well, and she pointed him to our paper as well. Anyway, so let me, I think time allows for that. Let me briefly comment on their papers as well. For J, it's this result is the center. It's a short paper. Priyanka and Manish, what they look at here in this proposition 1 is, and what they look at the proposition and say, oh, you know, that looks pretty bad. However, we know there's at least one mechanism that is strategy proof and envy free, and that's equal division. And now they ask, in light of this negative news here, is there really anything that is better than equal division? And then they identify ways in which to improve upon equal division in pairwise traits that still leave you with strategy proofness and envyfreeness intact. And they investigate how far you can get using this technique. And that's basically, after this initial overlap, that's where our papers then part ways. So there's another second impossibility result right here that strengthens the first one, namely provides a quantitative bound on how bad things have to be. And while unanimity demanded that in these special instances we provide everyone with their most preferred object with probability 1, a natural way to weaken that is to say, well, at these special profiles at least, everyone should receive their most preferred object with probability q. Right? Another thing as a prerequisite for the next result is the following requirement. We consider an extremely weak notion of non-wastefulness, namely one that not only looks at the ex post, at the eventual allocation and in an ex post perspective, but where we restrict notions of waste to comparisons involving unassigned agents. So we typically would consider to be wasteful if an agent receives an object, but another one that they like better is in the end unassigned. We weaken that further and say we only consider it waste if that agent is also unassigned. And then we have the following mechanisms satisfying this weak wastefulness notion, strategy-proofness and envyfreeness can be q-unanimous at most with q 2 over n. That's the second statement here. The first one, whereas unanimity looks at profiles where there's heterogeneity in preferences and that everyone has a different most preferred object. You can think of other preference profiles where there's the least amount of conceivable conflict between one individual on the one hand and all others on the other hand. And those are profiles where one individual has a top ranked object and everyone else ranks this object last. In those instances, how much should the one individual who prefers this object, with what probability should that individual be assigned that object? And here again, the answer is at most 2 over n. And now I think I briefly mentioned that this actually strengthens the first impossibility result. You might be skeptical and say, you know, we have this non-wastefulness notion here introduced, but a mechanism that would have been unanimous, strategy-proof, and envy-free also would have been non-wasteful. In that sense, it is indeed a weakening of the first negative result. Now, to show that it is tight, these two bounds are actually tight. I briefly, you know, what's my deadline? Is it 12:50 or?
It's 53.
It's 50. Okay. Anyway, yeah, very simple mechanism. We dub it a random careless dictator mechanism for reasons that I think will become obvious. First, let's drop the random part perhaps and consider mechanisms phi I. Might call them careless dictator mechanisms. What we do there in such a mechanism phi I is we pick individual I. Whatever their preferences are, they get their most preferred object. And then all the remaining objects are distributed uniformly among all the remaining individuals. Now, if we now randomize over these phi I, pick the dictator uniformly at random, then this is what we call the random careless dictator. I think it's quite immediate that this is better than equal division. So everyone does better than under equal division, at least if you're a dictator, your preferences are included or are respected. And that more than compensates for the fact that someone else as a dictator might take your object if they get to choose first. Second of all, it is dominated in turn by the random serial dictatorship, where you don't stop after one round, but continue also respecting the preferences of individuals further down the line. Okay, and you might have guessed it, this mechanism satisfies both bounds that we had earlier. It is exposed weakly non-wasteful, strategy-proof, envy-free, and in these special instances, at these special profiles, individuals do receive their most preferred object with probability 2 over n, which is not much, but it is the best you can do. Third, no, second, okay, one more thing. If you drop the exposed weak non-wastefulness requirement, if you are content with situations where eventually we have an unassigned agent and an unassigned object, even though that agent finds the object desirable, if you're content with that, you can actually increase the bound on q-unanimity here. So it depends on the context whether waste can be accepted and how much you really, on the other hand, think of efficiency in terms of reflecting individuals' preferences on the other hand, on who gets what object. Okay. We do have a characterization of the random careless dictator in using one additional property, but it's only for n equal to 3. The one additional property that we have here is weak efficiency, so standard weak Pareto efficiency that would require that it's not possible to make everyone strictly better off. And an ex post weakly efficient mechanism is simply a mechanism that randomizes only over such assignments. And if we include that as one more requirement, so we have in an ex post sense both the weak non-wastefulness and the weak efficiency, then together with strategy-proofness and envyfreeness, we do find that for n equal to 3, the random careless dictator is the unique mechanism that satisfies these. Last result. if we move on from the domain where so far we stayed, where all objects are acceptable, and now allow for the fact that individuals might actually prefer to remain unassigned over at least being assigned some of these objects, then as a superdomain of the one we previously had, the impossibility results of course stay intact, but more interestingly, we can change the initial impossibility result in the following sense. We replace unanimity by the exposed weak non-wastefulness and arrive at the following result. In general, on this full domain, if we insist on strategy-proofness and envyfreeness, then we have to accept waste in this very strong sense. So we cannot even achieve exposed weak non-wastefulness. And that corresponds to the result by Martini on the very same domain, where he used a stronger fairness concept, a weaker fairness concept, namely equal treatment of equals, and found incompatibility with a stronger non-wastefulness concept, namely non-wastefulness in an ex-ante sense and in the traditional sense where you care about individuals independently of whether they are already assigned or not. Yeah, and that's it. We do have a quantitative upper bound on efficiency for mechanisms that are strategy-proof and envy-free, show that it is tight by introducing this new mechanism. Not, admittedly, it's more of a theoretical interest, I would say, than of practical interest. We do have this characterization, at least for the case of n equal to 3, and the new impossibility result on the full domain. Yeah, that would be it from my side. Happy to answer questions and see you over coffee.
Thank you, Christian. So I have a question. Any ideas about the problems of larger sites? So whether your mechanism is still going to be tight there or not?
Come again?
Do you have any ideas about the problems of larger sites? So you have a characterization for 3 agents.
So in the paper, I stopped the sharing. Didn't I? Okay. Okay. So the bound here is now for general n. In the paper, we still had this proposition here only for n equal to 3. Now it's for general n. And together with proposition 3, which is also for general n, yes, the answer is the bound is tight for general n.
Okay, I see now.
But yeah, it's in the paper we still had proposition 2 only for n equal to 3. We recently generalized it to general n, and should hurry up with the working paper.